Welcome to MEI Mechanics. We're on the topic of mechanics basic principles, and this is video 1.7, equilibrium of forces. So in this video we're going to be focusing on Newton's first law, which says that a body will move with constant velocity in a line, or it will remain at rest if there is no resultant force acting upon it. And so we're going to be dealing with situations where we've got a body which we know to be at rest, and apply Newton's law, which then tells us that all the forces that are acting on it must sum to zero. And we can use that to solve problems and to find unknown forces and so on. Now, this is going to involve resolving forces again, so just a reminder from what we said in the previous video that if we have a force which is making some angle to, in this case, a horizontal and vertical line, although they don't necessarily in that orientation, though they will always be at right angles to each other, the two components that we resolve into, then because we've got an angle theta here, this vertical component is f sine theta. We associate the sine function with being opposite an angle, and this component is f cos theta. So we can always resolve this force into these two components. Now here's an example of this. So we have two unknown forces in this diagram, P and Q, acting horizontally and vertically respectively, and what we're told in this problem, and this is really important, is that the system is in static equilibrium. Alright, now that's a fancy way of saying that the overall force is zero, and so this particle is not accelerating. And what that means is that if we can resolve these other two forces into their horizontal and vertical components, then both the horizontal components will add to zero and the vertical components will add to zero as well. And that will allow us to work out what P and Q are. So why don't we start with the this force here, and we can resolve it into a horizontal component and a vertical component by drawing a right angle triangle on the force, similar to what we saw in the previous slide. And that means that this component here, this vertical component, is 10 sine 50 degrees because that's opposite the angle, and this horizontal component here is 10 cos 50 because that's adjacent to the angle. And then for this force down here, it will have a vertical and horizontal component as well. The horizontal component is opposite the 70 degrees here, so we can say that is 7 sine 70 degrees, and the vertical component is 7 cos 70 degrees, acting downwards of course now. So let's start with the horizontal components. We'll define right as being the positive direction. So if we add together the forces acting horizontally, we have 10 cos 50 degrees plus 7 sine 70 degrees. And because Q is acting to the left, we have minus Q. And because we're in static equilibrium, they must add to make zero. And so we can rearrange that for Q. So Q will be 10 cos 50 plus 7 sine 70, and that works out as 13.0 newtons. In the vertical direction, we'll define up as being positive, so we can say we've got 10 sine 50 newtons, and then remember the 7 cos 70 is acting downwards, so we have minus 7 cos 70, and we have minus P, and again they must equal 0 as well. So rearranging that, we find that P is equal to 10 sine 50 minus 7 cos 70, which is about 5.27 newtons. OK. Here we have another example, more of a sort of real life situation. So we have a rough slope with a box at rest on the slope, and that is crucial, the fact that we're told that it's at rest. It's a 6 kilogram box, and the slope is inclined at 10 degrees to the horizontal, and we're being asked to find the frictional force and the normal reaction force. Okay, so if you remember, the frictional force, that always acts to oppose the motion that the object is either undergoing or would undergo if the conditions were correct. Now, because we're told this is at rest, that means that the friction is stopping the slope from stopping the box from moving down the slope. So the friction must be acting up the slope to oppose the motion the box would like to do, which is to slide down. So we can label the friction there, and of course the friction always acts parallel to any slope, and the normal reaction, remember normal means perpendicular, so the normal reaction force will also be perpendicular to the surface. Now what that means is that when we're dealing with resolving forces in a moment, it's going to be sensible to resolve the forces not in horizontal and vertical directions, but in the directions parallel and perpendicular to the slope. And the only other force which is acting here, of course, is the weight of the box. Now that always acts vertically downwards, that doesn't depend on the slope, and of course that's mg, so that is 6g acting downwards. Right, so what we need to do then is we need to resolve this 6g into into two components. So there will be a component which is acting down the slope, parallel to the slope, and a component which is acting perpendicular to the slope, like that. So we can form this right angle triangle, and if we spot that this angle here is 10 degrees, that means that this angle here is also 10 degrees. So let's label that. And this component here then, because that is opposite the angle, that is going to be 6g sine 10 degrees, and the other component is going to be 6g cos 10 degrees. Now, we're ready now to apply Newton's first law. Because this is at rest, we know that those forces must balance. So let's start with the thing which is going to give us the frictional force. If we define up the slope to be the positive direction, then we've got F, which is acting in the positive direction, and we have minus 6g sine 10 degrees, because that 6g sine 10 degrees is acting downwards, or down the slope, and that must equal 0. So that tells us that F is equal to 6g sine 10 degrees. Remember, g is 9.8, so if we work that out, find that F is equal to 10.2 newtons. Let's now turn our attention to R. So again, we need to choose a positive direction. If we choose the direction that R is in as being positive, then we've got R minus 6g cos 10 degrees equals 0. And so R is equal to 6g cos 10, which is 57.9 newtons. Now here's another example. This time we've got an 8 kilogram mass which is hanging from two light strings. And we're asked to find the tension in each string. So each string will have a tension in it, which will be causing a force on the object. So there will be a force, and the tensions always act when the tension from a string is acting on an object. That force on the object has to act in the direction of the string. So there'll be a force that we could label T1 there, and another force which we can label T2 there. Now what's nice about this question is if we look at these numbers for the angles, 65, 25, they're up to 90, and that means that this angle here must also be 90 because the angles on the straight line add to 180. And that helps us somewhat because it means we can resolve the forces in the direction of T1 and the direction T2 separately. If they weren't at right angles, it would still be possible to do this type of problem, but you'd end up with a pair of simultaneous equations, so it would be a little bit harder in terms of the algebra, but it could still be done. The other force which is acting on this object is the weight. It's 8 kilograms, so it's 8g. That's its weight. And it doesn't completely make this obvious, but it's hanging. I suppose we can assume here that it's at rest, and we're going to need to assume it's at rest in this question. And so when we resolve the components and we look at the components in the two different directions, we'll find, just like in the previous two examples, that they add to 0. So we need to think about how we can resolve this 8g. If we think about the directions that we're dealing with, we've got this direction and this direction, so I want to form a right angle triangle with those two directions forming the two shorter sides like that. So that there, well, we need to think about what angle we have. If we look at the angles we have here, we can see that this angle of 25 degrees must be this small angle here, and this 65 degrees must be this angle here. We could choose to work with either of those angles, in fact, and that's always the case in a right angle triangle, because you can always work out what the other angle is. So let's just make a choice, and let's work with this one. So that's the 25 degrees. And so this component here is opposite the 25 degrees, so that is 8g sine 25. And this component here is 8g cos 25 degrees. So if we start with T1, in the direction of T1 we have T1 minus this component here, which is acting in that direction but in the negative sense, so that's T1 minus 8g cos 25 equals 0. And so if we rearrange that, we find that T1 is equal to 71 newtons. Now that is just given to two significant figures, and there's a very good reason for that, and that is that the number that we're using for G of 9.8 is only correct to two significant figures. And in fact, the value, if you were to look to three significant figures, you find that the value of G changes depending on where you are on the surface of the Earth. So it doesn't really make sense most of the time, unless we want to be really precise and talk about a particular place on the planet. It doesn't really make sense to talk about G to any more accuracy than two significant figures. So it's sensible to give your answer to two significant figures. Right, so then if we look at T2 then, so again let's say that that's the positive direction, so we have T2 acting that way, and then we've got minus 8g sine 25. And overall that must equal 0. So rearranging that, we find that T2 equals 33 newtons, and again that is correct to two significant figures. So that concludes video 1.7, and concludes the topic of mechanics basic principles.